Okay, so you can check over your solution here. So at t equals 8, I'm ending up with 59.366 degrees. Okay, so again, every iteration, I need to calculate my slope, which I'm using this differential equation. Okay, so these are my slope values I've calculated. There's one more slope here that I haven't highlighted. Okay, so these are my slope values that I'm using to calculate the change in temperature, and then using that, I'm getting the next iteration of this. Okay, so we can actually solve this differential equation because we have solved this. These are ones that we did last day or a few units ago. So my dt by dt time is equal to negative 0.05 t minus 20. Okay, so I'm going to separate and integrate this. And I have initial condition of t equals 0 at 80 degrees Celsius. So there's my differential equation. I'm going to separate and solve. So I end up with d big T, or temperature, over t minus 20 is equal to negative 0.05, the change in time. Integrate both sides. I'm going to end up with log t minus 20 is equal to negative 0.05 times t plus c. Okay, so then solving this differential equation for t, I get t minus 20 equals e to the negative 0.05 t plus c. That plus c is going to show up as a k value in front of the variable, so it's going to be k e to the negative 0.05 t. Okay, so I'm going to solve for my k value by plugging in. I'm going to plug in my t equals 0. My temperature is 80, so at a temperature of 80, we have my t value is 0. Okay, which then makes my k value equal to my initial temperature difference. So k is equal to 60. So my equation then looks like this. My differential equations, the solution to my differential equation is going to be 60 e to the negative 0.05 t, okay, plus 20. Okay, so, and this is consistent. When I plug in t equals 0, I get 80 is my starting temperature, and this is an exponential decay of this temperature. Okay, so this is my Newton's law of cooling. Okay, so the last one here, we're going to use that Euler's method again to calculate the solution to this differential equation. Okay, so we're going to then start with my x equals 0, y equals negative 2. Okay, so those are my values here. When I calculate my slope, my initial slope, when I plug in 0 for x, negative 2 for y, I get 1 over e to the 0. So I get an initial slope of 1. So my first iteration of this is going to be my y value, and I'm going to approximate my y value at since my delta x is 0.1. Okay, I need to know my slope. Okay, my slope is, I have a slope of 1. My change in x is going to be 0.1 minus 0. So remember that this essentially represents my change in x. Okay, and my initial y coordinate is going to be negative 2. So calculating my new y coordinate, I'm gonna end up with, this is going to be 0.1 minus 2, so negative 1.9. Okay, so that's my first approximation, is negative 1.9. Okay, so I need to now calculate my new slope. Okay, so my new slope is going to be a little bit messy. So calculating my new slope, I'm going to plug that in again. So it's going to be actually it's just going to calculate the e part first. So e to the power 0.1 minus 1.9 plus 2. Okay, so that's going to be, and I want the reciprocal of that. So my value for my slope value, what I'm going to end up with is I'm getting 0.81. I'm just going to round this to 3 decimals. Okay, 819. Okay, so there's my next iteration. And I'm going to use that then to come up with my next equation. So I'm going to calculate for x is 0.2. So y at 0.2, I'm going to use the new slope of 0.819 times my change in x, and my old y coordinate was negative 1.9. Okay, so then using this calculation, I'm going to end up with, let's see here, times 0.1 minus 1.9. Okay, so I'm going to end up with negative 1.81, about 818. Okay, so there's my new coordinates, negative 1.818. Okay, so we'll do this for one more iteration. So that means I need a slope for the next point. So I need to calculate my slope. Okay, so I'm going to use that equation again. So it's going to be e to the power. X is going to be, in this case, 0.3. Okay, plus okay, so it's going to be minus 1.818 plus 2. Okay, that's my, and I need to know the reciprocal of that. So I'm getting a slope of, it looks like my slope works out to be 0.61, about 618. Okay, so there's my new equation. I'm going to write my new equation to calculate the last value here, 0.3. So my slope is going to be 0.618 times 0.1, and then my coordinate is going to be negative 1.818. Okay, so I'm going to use that slope times 0.1. So I'm getting the last coordinate here is going to be negative 1.756. Okay, so there's my Euler's approximation for the last one. This one happens to be a separable equation, so if you really wanted to, we could write this as a separable equation like this, dy by dx is equal to 1 over e to the x plus 2, and then e to the y. And then we can actually separate this and integrate this. So we end up with e to the y dy is equal to dx over e to the x plus 2. Integrate both sides. Okay, this is going to end up being e to the y is equal to, it's going to be e to the negative x minus 2 negative plus c. Okay, and then we can solve for this y. We can basically write this as e to the y is equal to negative e to the negative x minus 2 plus, well, that plus c, that plus c is going to be a real problem to solve for, so we'll just leave it like that. We'll leave this solution in that form. So that's our solution. We can plug in our x and y, our initial x and y of 0 and negative 2 to find out our c value. I suppose we can do that. Negative 2 equals, plug in 0, negative e to the negative 2 plus c. Okay, so we end up with our c value is equal to, it looks like 2e to the negative 2. So my equation works out to be e to the y negative e to the x, negative x minus 2 plus 2e to the negative 2. Okay, so this is a solution. The actual solution to my differential equation. Euler's method is giving me this solution to my differential equation. Okay, and again, we can draw our slope field, draw this in our slope field, and we can see how this is following our slope field, which then is just generalizing the solution to this, or approximating the solution to this differential equation, or sorry, to the general solution equation.